1. Hi, all. Welcome back to the Sigma Model Chronicles, Part 3, with Amr joining again. Thank you for joining, Amr.
Thank you, Vasu. How are you doing?
I'm doing good. I'm doing good. And how are you?
Good, doing all right.
Yeah. Well, we're now finally going to dip our toes into off-shell string theory. So, yeah, take it away, Amr.
Oh, thank you, Vasu. Okay, so I think this episode will start delving into the off-shell string theory papers, part one, and later part two with that Aaron and I wrote in the last month or so. But I think we'll go through the introduction together in the paper, and then it comes a point where we'll do shift to the Zetlin's prescription and try to motivate the derivative del by del log epsilon prescription, and then start explaining the Polchinski and Liu paper that basically dealt with the conformal Killing group, the infinite conformal Killing group of the sphere, and then come back to our paper again and see, and then maybe a little bit also about Zetlin's prescriptions and from his original papers, and then come back to what Aaron and I did to basically prove the consistency of the equations of motion and the off-shell action derived by Zetlin's prescription. Okay, so this is sort
Perfect,
of a rough plan of maybe one or two episodes. So let us go through a little bit of the introduction. And let me start by saying that I was in the strings conference, the last one in Vienna, which was, I believe, last June, I think. And then, if not July, maybe I'm wrong, maybe July. But then there was a discussion panel, and one of the three major challenges of our current understanding of perturbative string theory is how to define string theory off-shell. So this was considered as one of the main challenges, how to define strings in off-shell backgrounds. How do we take an off-shell background, a background that does not correspond to good formal field theory on the world sheet with a zero central charge? And how do we compute path integrals? How do we compute in such an off-shell background how to make sense? What is such a formalism, and how do we understand it, right? And it turns out that Arkady Zetlin, of course, back in the 80s, he developed the first quantized off-shell formalism that was used by Susskind and Obolum for the black hole entropy. And then this is the reason why we want to understand it, because it allows you to directly compute path integrals for string world sheet theories in off-shell backgrounds in the sigma model formalism, right? And using the sigma model formalism, as we will see that even when we tried, or not tried to prove it in this paper, we were not really limited or to basically sigma model conformal field theories, or deforming about a flat space vacuum, to be precise. And this was our starting point. So it's nice because, as we mentioned probably in the first episode, that they're very important backgrounds that we would like to get a sense of. We'd like to understand how strings propagate them. I mean, for example, like I said, a conical manifold. How do we make sense of that? There's no counterpart, or there's no conformal field theory of such a manifold. So how do we make sense of strings propagating in such a background? Or this would be important, for example, for the replica trait, if you'd like to understand the replica trait in string theory and such. Um, eh, Other backgrounds that are not even geometric
Right.
grounds, how do we make sense of them? What are these non-geometric backgrounds? How do you begin to define strings propagating in such a background? There are many questions. Maybe also, I don't know about that. Maybe de Sitters, because there's always a tension between de Sitters and string theory, as you probably know more than I do. But they're not compatible. There are many problems there. Maybe off-shell, maybe, perhaps I'm speculating that maybe off-shell string theory can shed some light on these de Sitter at some point.
And conceptually too, right? The fact this goes back to what we were discussing all the way back in, I think the first part, where we were just looking at the the calculation of the beta function, and we realized like, okay, these things look covariant, whereas the claim usually is that string theory is good for computing S matrix elements strictly, right? Like, being purely on shell is kind of like equivalent to being completely blinded to even the potential of having some background independence in the theory. You necessarily need to have this off-shell information. That sort of is where this whole flexibility of background independence lies. And I mean, to the extent to which there are sort of criticisms of the whole string program around the question of background independence and its role in quantum gravity, it mostly just has to do with the fact that you just don't know how to properly talk about off-shell things. Right, and that's really it. It's nothing more than that.
What does it mean exactly? What does it mean precisely? You always assume there's always a background, and which is on shell. The assumption that there is a background, that means the assumption there's something which is on shell that corresponds to conformal field theory.
Yeah, exactly. Yeah.
In a sense. But and then at some point maybe we'll discuss some other applications of off-shell string theory in the bulk, because as I want to remind you, whoever is going to maybe probably watch this episode, the point is the goal is, and maybe we'll talk about this later, is to bring this whole formalism of off-shell strings in holography, in the bulk, right? So we get a holographic interpretation of what it means and what off-shell string in the bulk. What is the potential? What problems can it solve that we cannot currently solve by focusing on shell strings, right? And there's a whole slew of problems that one can discuss potentially, and that is the goal, right? I feel like the off-shell community. I feel like it'll take a two-sided black hole, and then we have the holography on the left CFT, and then the off-shell community, first, second quantile, doesn't matter. String field theory included, of course, everything. All the off-shell community people work in off-shell physics on like the left CFT, and there's no wormhole or something connecting them at all, right? I mean, just there's nothing.
Right.
And I'm trying to bridge the gap between those two communities, the interesting developments that have been happening again in the last 15, 20 years in information theory and black hole information paradox, and see what can off-shell string theory say about these things, and without having to define non-perturbative string theory,
right.
without having to go through this. Okay, so this is the goal. So with this introduction, again, which something I think we discussed before, let us see what we say in our paper before we go to Polchinski and Liu to discuss the volume of the SL to C of the sphere. As we say here, an off-shell approach to string theory has multiple advantages. One of them is, the first one is allows you to directly derive a target space effective action from some string Walshy action, rather than having to deduce the action directly from equations of motion, right? So as usually we learn, from Polchinski, I think chapter 6 or something, you say, okay, what are some target space effective actions? And here are some equations of motion. And it turns out that the equations of motion that come from the world. So with the beta functions appear as as equations of motion of some target space effective action without us being told where the effective action comes
Yeah,
from.
it comes from, right.
So we're trying to make the link here. It also allows us to discuss, as you and I, of course, discussed before, endpoint correlation functions of massless fields. We're going to talk about massless fields for now, without having to take the LSZ limit where the insertions go off to infinity. Okay, this is the usual quantum field theory approach. It allows us to involve intrinsically off-shell constructions, most notably off-shell calculations of black hole entropy, which require introducing a conical singularity as one background that violates Einstein's equations, for example. So we will try to introduce the first quantized formalism of Zetlin, of Arkady Zetlin at Imperial College. Shout out to Arkady if he happens to view our episodes, of course. He's behind all that. And then we want to, so the first thing to say is that we are going to, Aaron and I, in our work, to explain these off-shell formalism, we want a conceptual justification, and we want to improve on what Zetlin did, and we're going to do that. We're going to use conformal perturbation theory, and to perturb around any CFT that could possibly be strongly coupled or highly non-geometrical, right? So in Arkady Zetlin's original formalism, as we're going to discuss, he's using sigma model as deforming of a flat space vacuum. So like a flat metric, constant dilaton, for example, but whereas in using alpha prime expansions, so beta functions or expansions in alpha prime. Here we're using conformal perturbation theory, starting from a C equals 0 central charge CFT, and which could be anything, and then trying to prove the equations of motion order by order in perturbation. And so that is one distinction between the proof, the formal proof, if you will, that Aaron and I have developed here versus the original formalism or the original approach taken by Arkady. Also, as I mentioned before, we're going to assume that the world sheet theory is a quantum field theory rather than a CFT, right? We're going to say that given the importance of conformal invariance to the consistency of the standard formulation of string theory, you might think that going off shell is going to introduce, well, it's not one thing. You actually going off shell will introduce ambiguities, right? Call them off shell data, and you're gonna say, okay, well, then this is not going to work, or this is some action. The action is inconsistent. But as we're going to actually see how we're going to see how this problem is beautifully addressed and solved in the sense that in the form of field redefinitions or RG schemes are going to be central to removing these, to discussing or addressing these off-shell ambiguities, basically. So here's the issue. The first issue is that we're going to see that these ambiguities are basically have to do with a vial frame on the world sheet. That when you fix diffuse, when you fix the vial, this is part of the standard string theory story action. When you fix a diffuse and you fix a vial frame on the world sheet, there's multiple wireframes after you fix the diffeomorphisms on the world sheet. But at the end of the day, you'll see that this arbitrary choice of a vial frame basically does not really matter, because the effect of changing omega or the vial frame can be fully absorbed into field redefinitions of the target space fields. This is crucial, a crucial point. So in other words, when you compute the path integral uh, um, in this formalism, you pick one particular frame. Okay, don't integrate over all vial frames. That is not the approach. You fixed one vial frame, which you can think, okay, well, it's ambiguous. Why this vial frame? Then your result, your action, and the equations of motion and everything will depend on your choice of the vial frame. And that's inconsistent. But as we're saying here, and as we're going to show, that dependence can be absorbed. The dependence on the vial frame can be absorbed beautifully into what on the world sheet is going to be our renormalization group scheme.
Right.
Or field redefinition in target space.
Yeah, but I mean, this is like kind of baked into everything we've said already, right? It's just the fact that, like,
Absolutely.
if the equations of motion are beta functions, setting aside the right-hand side, just the left-hand side of the equations
Right.
of motion, something equals zero. And then while invariance is beta functions equals zero, so something equals beta function, then what does local RG tell us the beta functions are? Well, they're the response to change of the while frame, right? That's kind of what they are. So, and on top of that, what do we need to do in perturbation theory in the bulk or in the target space? Well, we need to ensure that there's invariance under shifting by redundant operators. Like, these are the field redefinitions. Like, normally when we do perturbation theory, we're always assuming this. I mean, the whole BV formalism is based on just this insight, right? So it's all already there. It's just that you guys kind of really, I mean, the brilliance of you guys was that you cornered this, right? And that I think is very cool. Let's come back to that when we see it.
Yeah, absolutely. We'll have more to say more precisely about that. And now let us talk about Zetlin's prescriptions, Arcadi Zetlin's prescription, and the log epsilon, what is epsilon, and what is log. Now, we're going to focus on genus 0, the sphere. So Arcadi-Zetlin's prescriptions work beautifully, equally well, or higher genus, but they are particularly subtle for the sphere, which is the entire focus of the paper.
Right.
And the reason is, as people probably know, in string theory, when you compute using Polyakov, the Polyakov path integral using Polyakov's formalism, you for the sphere, after you have fixed the vial and the diffuse, there is this residual conformal killing group, SL2C, that you still have to fix, right? So for people who are hearing us, this is a standard string theory story. You fix the vial, you fix diffuse, introduce the ghost action on the sphere as well as on the torus, but it's not as problematic because it's compact. You still have a residual group that lives in like diff cross vial.
Right.
This SL2C is sitting in the denominator of the vial. We'll show that in equations in a moment. SL2C is a non-compact group, which means it has infinite volume. The standard way in string theory for a compact CFT is that, as we learn, we fix 3 points on the sphere. This L2C, right, is 3 complex dimension. It is the global conformal killing. It has special conformal transformations, translations, and dilatations, vial transformations, right? The L-1, L0, and L1. Global conformal killing group. You fix 3 points on the sphere to absorb or consume the entire degrees of freedom of the group. And then you say, I compute the 3-point function and 4-point function, but you never worry about the 0, 1, and 2-point function. You say they vanish on shell. This is the starting point, and building up to the Liu and Polchinski story here, right? Is that on shell, the 0-point function, the 1-point function, and the 2-point function, they vanish. We say the 0, 1, 2-point function, which is the sphere with no insertions, the sphere with 1 insertion, no tap holes, they vanish because of conformal invariance. So on shell. The 2-point functions vanish for consistency. Basically, there's no tree level uh, no tree level mass anomaly or tree level yes, there's
Contribution to
no
the beta function. Yeah.
mass renormalization or something like that, right?
Yeah.
But then you do the fixing 3 points is what we do in the standard string theory to deal with the problem of SL2C, right? So this is called the Mobius group, right? But in in the Arkady-Tetlin's prescription, you might, well, what happens? It's an infinite group. What happens if I decide to integrate over all vertex insertions? What happens? What's going to happen? So instead of fixing 3 points, suppose I have an n-point function. Instead of fixing 3 and integrating from 3 to n, what if I integrate from 1 to n? What's going to happen? And take some limits. And as points come close or approach or try to collide, and regulate that collision by some cutoff that you put on the world sheet. What happens? What kind of divergences? Of course, you expect you're going to put some cutoff, which has some size, to regulate the divergences as points come close together, as we usually do in conformal field theory. Then you expect some divergences to surface, to appear in the correlation function. These divergences will appear in some limits. Some of them will be quadratic. Quadratic are nice. They can always be swept under the rug. You can always find some scheme to absorb them by some analytic continuation or something. But the problematic ones, the real ones, are the log ones, the logarithmic divergences, because they appear at all scales, being logarithmic by definition. Sorry about that.
No worries. Yeah.
So then
we should maybe linger a little bit just on the previous point of where SL2C came in for, if you have a little bit of a break here, to say that the reason it appears from the perspective of sort of textbook string theory is that we're doing a two-dimensional quantum gravity path integral in addition to having some matter, some conformal matter.
Yeah.
And there you see we have the diffeomorphisms of these two dimensions and the Weyl transformations, which we're trying to treat as gauge invariances.
Yeah.
And just as how killing vectors, so if you think about the relationship between diffeomorphisms and killing vectors, you realize that, well, killing vectors are like, you see, if you're thinking of taking a quotient, killing vectors are a bit of a problem, even from the perspective of diffeomorphisms. They give rise to essentially fixed points under the action of general diffeomorphisms of particular points in the space of solutions, because that's what an isometry does. It just, the lead derivative under some vector field just, annihilates that metric,
Yeah.
Now we have an extension of this phenomenon with the Weyl group's action in addition, right? So those are like not just killing vectors, now they are conformal killing vectors, where we're not just accounting for the possibility that there's a lead derivative action that the metric changes by, but there's also a pointwise multiplication by positive function.
Yes.
So the problem, or the difficulty, what can lead to issues when we think about quotients are like fixed points under this joint action, which will lead to conformal killing vectors. And for the sphere, those conformal killing vectors are SL2C, the Mobius group. And that's what we're contending with right now. And the counting you said of like 0, 1, and, well, 1 point, 2 point functions and 3 point functions, so all that stuff, I mean, when you said that you have this consistency, conformal invariance requires that you don't have the 2 point function appearing. Just to recap, it's because always beta functions start, right, with a sort of dimensional analysis factor almost. You just have a factor that comes from the dimensional analysis that knows only about the data that would be in the 2 point functions at the fixed point, right, if you're doing conformal perturbation theory.
Yeah.
And that's the thing that would have to also vanish necessarily if you require true Weyl invariance to be instated.
Absolutely.
So this is the reason why you have 0 2 point function, but also that structure has a very similar feel to what we would think of as a propagator, the kinetic term,
Yeah.
which again you're gonna come to, I know. And
This,
so
mhm.
this is like, yeah, so this is like all these different notions coming together, and I feel like to sort of break it up into the pieces we've already seen, we already have a very coherent story that motivates why we're worrying so much about SL2C at this point in time.
Absolutely. So of course, one could start from from the very beginning, explaining the where the conformal killing group comes from after he picks the diffuse and do Fabir probe and introduce the ghost action, and then symmetric will have these which are gauge transformations. I assume I thanks for going over this, but if you'd like us to go over this from the SL2C story, where does it come about, where's the origin, we can do that, but it will take
No, sure. I think that, yeah, just I think that should be adequate.
yeah, introduction to that. So
Introduction
so
runway.
then yeah, so then the act that now, if we want to construct, and I promise this will all be done in equations at some point. If I want to construct, so I compute correlation functions by integrating over all the points, right? This would go some over. I integrate over points. Now I introduce a cutoff on the world sheet as points come close together. As points come close together, if we compute an endpoint function, then I'm going to have quadratic divergences and I'm going to have logarithmic divergences, right? And one central issue is how to subtract or renormalize those divergences that appear in endpoint correlation functions, right? The point is, from the endpoint correlation functions, I want to construct a partition function as a generating functional, right, of these partition functions for massless modes that are incoming, but with very small momentum. So we're going to assume massless modes. There are going to be marginal deformations, and they're going to have small momentum, right? Because marginal means you have zero momentum, but now we're going to have non-zero momentum, which are small, right? Small incoming momentum, and and then we're going to have to see how we subtract those divergences, because the ultimate goal is to construct an off-shell partition function in target space that acts as a generating functional for these endpoint correlation functions. That, just as we said, these endpoint correlation functions will have divergences. And the ultimate goal is to construct an off-shell action without poles. You cannot really, doesn't make sense to construct an action without poles. You construct an action, you need to construct an action without poles, away from poles of correlation functions or S matrices, right? You want to basically do certain things. You also want to be able to extract or to check or to verify that from the endpoint correlation functions, which are off shell, that when you go on shell, when the external legs of your endpoint correlation functions are truncated, come on shell, basically using some LSD prescription or something, that you recover the standard results of the S matrix, right? And then, and the action itself, so these are poles, right? And the S matrices have poles, but the action cannot have poles. The partition function of the sphere of the path into the partition function that you calculate from the world sheet, and ultimately the target space effective action that you derive from the path integral or the world sheet partition function, should be constructed without any poles in them. No logarithmic poles, nothing, right? And so, and here's the thing, if I'm going to integrate, so that comes back to the original question. If I'm going to integrate over all insertions and introduce a cutoff, I'm not going to fix 3 points anymore, as we do in the on-shell prescription. I'm not going to fix any 3 points. I'm going to integrate. How do I remove the poles, the log divergences, and the quadratic divergences from the correlation functions, right? And therefore, from the partition function, which is a generating function of all of them, such that I construct a consistent target space effective action. And Arkady Tsetlin's off-shell, first quantized string theory prescription is, broadly speaking, or prescriptions are, broadly speaking, a prescription to construct, to remove these off-shell, to remove these log divergences from the correlation functions, and thus from the generating function and the effective action when you construct four massless closed bosonic string modes. There's others for the disk and others for supersymmetric, but they are, broadly speaking, in a nutshell, a prescription to remove these divergences from the correlation functions and therefore from the partition function, such you have an off-shell, a consistent off-shell effective action that is free of poles. And then you can check that the beta functions, as we mentioned before, of the target space of the worldsheet sigma model become the equations of motion of the target space effective action, and therefore the Weyl consistency conditions, what we call the Weyl consistency condition, is satisfied. Yes. In a nutshell, these what our Arkady-Zetlins prescription are. And therefore, we see in the prescription that there are the first, what we call T1, which is the most famous one, the log divergences. These should be very familiar from the Calvin-Semanzic equation. These are log divergences of the Calvin-Semanzic equation, as we explained before. The local RG equation is at the heart of the Arkady-Zetlins off-shell prescription, and the function, they're baked into them, right? And so let us define this object K0. We use a little bit of different notation than the standard notation used by Arkady in his original papers. K0 is what you would basically calculate from the worldsheet partition function. So it's a sum over all the endpoint functions. So it's a sum over K0n. 0 here is the genus 0, and n is the number of insertions, right? And then you apply this operator, del by del log epsilon. This is an operator, right? It looks like an RG operator, and it is an RG operator. So those who have seen the local RG equation, yes, this is the generator of infinitesimal RG scale transformations on the world sheet. Yes, it is. Yes, it is, and it will be made precise in later in this episode. And then what you get on the left-hand side, so if this is the partition function of the sphere, so this is the, this is the sphere partition function, sphere, worldsheet partition function. And here is what you get is a target space effective action, target space.
This is one more concept here, which I think we didn't really get to, and it's a bit more of cult literature perhaps, but there's this very nice work by Dolan where he talks about a Hamiltonian version of RG flow equations. And he writes down effectively this Hamiltonian system. And what this is actually giving you is how should I put it? A formula for this RG Hamiltonian of Dolan's. So Dolan's RG Hamiltonian is effectively, it's like trace T, right? It is beta dot O effectively, in a flat space. So it's interesting. I hadn't thought about this before just now, but I realized
this is in fact going to be exactly related to beta O.
Yes.
So as we will let me come to that, but precisely this is going to be related to this.
Great. Yes. No. So this is Dolan's RG Hamiltonian density. So yeah, no, very
good. I'm glad you brought this up. So indeed, this is going to be related to beta times the 1-point function of the vertex operator. When you get into the weeds of this, yes, indeed. So this is where the del by the log epsilon prescription, and now we're going to mention why there's a log epsilon, but we just hinted to that. These log epsilons will appear in the endpoint function. And so subtracting or removing the log divergences from all the endpoint functions, remove them necessarily from their generating function, and I construct an effective action that is free from poles. So there's more to say, but broadly speaking, this is what we're going to do. Now, Arcadi took the quantum field theory on the world sheet to be a nonlinear sigma model, which we have been discussing so far, perturbing around flat space vacuum. So flat space vacuum basically means flat metric, no B mu nu, no electric and magnetic fields, basically, and constant dilaton. And he checked that his prescription gives good answers for the first few terms in the effective action, at least for massless fields in superstring theory. And we talked about the regime where basically the characteristic radius of the curvature is much, much bigger than the string length or alpha length. This is the nonlinear sigma model regime, right? But when we check the consistency of the action of his prescription, we're not going to assume that the quantum field theory is nonlinear sigma model. It's going to be something different. And the CFT will be something, doesn't have to be a flat space vacuum, it could be anything. Before we get into the second prescription of Arcadi, which looks like this, which is even more powerful, what we showed, and this is indeed something that any off-shell prescription should show, at least I think broadly speaking, is that you need to show that this prescription is able to recover the on-shell results, right? In some on-shell limit. So suppose you're off-shell, and we're going to define the sense now of some on-shell limit. We're going to define that. So when you go back to this, take this on-shell limit, you should recover from the endpoint correlation functions, the S matrix, because this is the thing we can only compute in string theory. And you should recover, you should check that there's some sense of an on-shell limit that you can take in your off-shell action or correlation functions, such that you can recover the standard S matrix results. And this is something we do in our paper. We're going to get that, but this is something we check. Another thing we check is that that you can recover an approximately local action for light string fields. Not very massive, not massive, right? Very light, and we'll define that. And show that the actions equations of motion are satisfied even only if the beta functions vanish. This is extremely important, and this is one central result in our paper, and on any off-shell prescription. So you cannot tell me that the equations of motion are satisfied and the beta functions, right, do not vanish. As I explained before, this means basically that you do not have a quantum, you have a quantum field theory, don't have a CFT, but it corresponds to some string theory solution in target space. String theory solutions correspond to CFTs, conformal fixed points. Conformal fixed points correspond to string theory solutions. These two must be checked. These two must be checked order by order in conformal perturbation. And that's what we do. We check that to all orders in perturbation. And this has to be checked. Otherwise, your off-shell formalism is inconsistent.
Right.
And I'm not going to go more into the details of the work, but I will say I'll start from here, and then we'll go to Polchinski and Leo right away. Okay. Then we'll talk about the SLPC. So let's start from here, and then come back to the rest of the paper. But to be a little bit more precise now, suppose I give you I start from bosonic string theory, and I give you the following partition function. The following partition function is an integral over the strings X, the world sheet metric G, And then in the denominator, we have the diff cross vile as gauge invariances, symmetries of the action, and then I get the exponential of some conformal field theory action as a functional of x and functional of the world sheet metric G. As usual, when we have gauge symmetries in quantum field theories, we need to fix, we need to gauge fix, right? So what do? The diff and the vile are non-compact. So this vertical bar, we better think of it as quotienting out, be quotienting out by diff cross vile, not dividing by them. And we'll see even this is why this is the right to think about it. The vertical bar is better thought of as quotienting out by the field space of the symmetry group rather than dividing by a number. So it's better to think of this as quotienting out rather than by dividing by a number. It's really important, and it's going to come to our third central result of our paper, which is the gauge orbits. And how do we deal with the SL2C, right? Good. So then you do this properly, you're going to have some covariant measure, dc, d omega, and then you know that the combination of measures, dg over d epsilon t omega is what which is in the ghosts, is what going to give you the minus 26 conformal anomaly, and that's why you need to introduce 26 bosons to cancel the anomaly, the standard story of quantizing string theory. Good. I'm going to get into that. LCFT is the Lagrangian of a conformally invariant theory. If you are on a string background, the path integral taken as a whole is invariant under diff cross vile, and you mod out by the group. But for the sphere and the torus, by the way, there's this conformal killing group. So suppose you have done that, you fix the diff, you fix the vile, you're still left with the conformal killing group. And of course, you still integrate over the ghosts, the anti-ghosts, and some extra whatever moduli space integrals you need to do. Good. Now let's focus on the sphere. On the sphere, in the case of G to 0, the Teich-Mueller space of the tau is 0. Don't have any moduli space. 0 has no moduli space, right? And this is no. You just fix the sphere itself, the 0, 1, and 2 point functions, because we're going to have 0, 1 point functions, so they have no moduli space, but you still have moduli spaces, dimension or non-zero moduli space when you have like 4 point functions.
Right. So when you add punctures, then you have.
When you start having punctures, then you have a moduli space. A dimension of M04 is like 1, right? And so on and so forth. Or if you're real, it's 2 real or 1 complex, depending on if it's a real or a complex moduli space. But in Arkady-Tsetlin's way, to give people heads up, we do not fix 3 points. So the sphere will have a non-zero dimension of the non-zero moduli space, even for less than 3 punctures, because we integrate over all punctures. Okay, so this will introduce some funny objects, some funny thing that the prescription is designed to remove by default. So the conformal killing group, SL2C, is a non-compact. So naively, the effective action that you construct from the partition function is 0. K0 would be this object without this. So I'm computing everything without the conformal killing group. So that's K0. But then if I divide by SL2C, which is infinite, then I get what? On shell, I get Z0 equals 0. But this is the correct answer only when where on shell, that is to say when the world sheet theory is a CFT, and only also correct when there are no vertex operator insertions. Okay. And this is because what you and I discussed before, this infinite volume of the conformal killing group is related in target space to the fact that the dilettante equation of motion is proportional to the action itself. Right? As we discussed before, modulo a boundary term if you have a non-compact target space. If you have a non-compact CFT, then you're left with a boundary term. For compact CFT vanishes on shell because of the dilettante. See, naively speaking, the non-compactness of the SL2C, the fact it's infinite, on the world sheet, the counterpart of that is the fact that the action, that there's this global symmetry of the dilettante in the target space. So you can basically translate, has this global translation symmetry of the dilettante, and that makes the dilettante equation of motion basically proportional to the action. And so when the equation of motion is satisfied, the action vanishes. This is the manifestation of this infinite SL2C volume, naively speaking, on the world sheet. Okay. But if you go off shell, that I don't have a CFT anymore, then this object does not vanish. I mean, because of the dilettante equations of motion. And so to calculate I0, we need a prescription for dealing with the conformal killing group off shell. In other words, if we're claiming that the space-time manifestation of the infinite volume of the conformal killing group, right, is basically that the dilettante equation of motion vanishes, is a total derivative, is proportional, that the action is proportional to the dilettante equation of motion, so it vanishes when the dilettante equation of motion is satisfied. Then if I don't want a vanishing action, then I better know the source of the problem. The source of the problem on the world sheet is that the conformal killing group is infinite. And how do we deal with infinite objects? Usually, we regulate them. As simple as that. If you have something that is infinite, regulate it. Put a cutoff, regulate it, introduce divergences, and deal with them in a renormalization growth pattern. Period. And this is precisely what we're going to do with the SL2C. Okay, so now let's go to the SL2C story and see how this was done by Joe Polchinski, John Liu, back in 1987, I guess. So let us go through. Let me erase my notes. What they say in this paper. Very, very important to go over even the first paragraph in their paper for understanding arcade acceptance prescription. It's critical. What they say is that to eliminate the conformal killing group, now there's going to be two cases. We have the sphere for closed strings and the disk for open strings. The conformal killing group is compact and diverges, the volume diverges. And in most scattering amplitude, the sphere with at least 3 closed string states and the disk with at least 1 closed or 3 open string states, the divergent volume of the conformal killing group is offset by divergent integration over vertex operator positions. Oh my God, this is just the leading up a non-zero results. Okay, this particular statement was Polchinski, Leon Polchinski telling us, hey, to actually offset the infinite volume, the conformal killing group, guys, you don't have to fix 3 points.
Right.
You basically integrate, put a cutoff. We're going to have and regulate the conformal killing group volume. Integrate over all vertex operator insertions. You're going to have some log, again, some divergences. If you remove these divergences by subtracting them or dividing them or something, then you have dealt with the conformal killing group. So it's giving us here two options. One, which our colleague Zetlin runs with in his prescription. So let me make that very clear. This is one. One is how to deal with the SL to C. One is integrate over all insertions, right? Regulate the volume, the SL to C volume. Well, no, I'll say integrate over all insertions, and then I'll say take some limits, and then remove those divergences from correlation functions. Here's one way, but we're not taught this way. We're taught the second way. The CK invariance is fixed position of some vertex operator insertions and remove the divergence from the numerator and the denominator. Okay. So this is something noted by Polchinski and Liu, and they say the following. Let's focus on what they say on this about the sphere. Say the vanishing of the sphere 0 and 1 point amplitude is consistent with the tree-level stability of the vacuum. No tadpole. Basically, they come from conformal invariance. No tadpole, no 1 point function. The 2-point function vanishes, or 2-point amplitude, I keep saying functions, basically the right things to say amplitudes, are the tree-level mesh shifts. We're not allowed a tree-level mesh shift. Although we can discuss also some paper that appeared within months of this paper, 2 or 3 months, by Nathan Seidler, in which he combined, discussed quantum mass renormalization.
Yes.
By combining the 2-point function of the torus, the 2-point function of the sphere, the 3-point functions of the torus by 3-point functions of the sphere to give a finite result. Really cool. About the same time, and very, very related to this. Very related to this story. And there's another paper that does exactly the same thing by Ashok Sen using BRST formalism. Now they talk about tubes on the world sheet, which I'll get to in a moment, because there we talk about degeneration of tubes. Long degeneration of tubes and these kinds of things. And this is how we connect the stream field here. What's happening? Okay, so we'll come to that. But you already see that Polchinski is saying that K00 equals K01 equals K02 is equal to 0 on shell for CFT.
Right, right.
Good. However, the disk 0-point amplitude should not vanish, and I'll discuss what this means, because there's something called the soft dilaton theorem, that basically says that the 0-point amplitude of the disk is equal to the 1-point amplitude of the disk, and this fixes some ambiguity on the disk that is there, and there's no counterpart of such theorem on the sphere. This is the most confusing result about the sphere and what people call the sphere partition function ambiguous, is because there's no, they would think that there's a counterpart of the self-dilaton theorem that basically says that the disk dilaton tadpole is proportional to the disk amplitude and fixes the coefficient or the ratio between them. But we'll come to that because, in fact, Aaron and I, in our paper, we discussed something called, in the section embedded within chapter 6, called the course footy, dilaton schemes. It's very technical, a very technical section that basically shows that why the sphere partition function is non-ambiguous, basically. And sometimes the 0-point function is proportional to the 1-point function, depending on how you look at it. It's the course footy dilaton schemes in section 6. It's something which is a very technical section, but maybe we'll come to it later. Now, let us see what else is Polchinski and Luer saying. They're saying something really cool. They're saying that if I put a cutoff on the sphere, on the SL2C, sorry, in the SL2C. So suppose I put a cutoff on the group as a manifold. Then the integrations over positions diverge. And this divergence is exactly the conformal killing group volume. So here's a hint, again, to Arkady-Setlin's off-shelf prescriptions. He's telling us that the divergences that you get from integrating over positions will diverge. If you put a cutoff, a small cutoff, you integrate over all positions, they diverge, and this divergence is exactly the conformal killing volume of the group of the SL2C, and then you need to come up with a prescription to remove those divergences. Arkady's way was, no, do not divide by the log divergence. It's going to be log divergent. Please take the derivative. Okay, so now I'm telling you the first time that he was telling us, do not divide by the log divergence of the conformal killing group. This is wrong. Rather, take the derivative of the log divergence, and there is a reason for that we'll come to later. Okay, so in other words, here's Polchinski telling us that integration over positions divergence, and this is precisely the conformal killing group volume. Instead of getting the amplitude of the sphere with n insertions, as you might have thought, 1 over the log, they were going to find log divergence in the correlation functions, something like this. I'm going to write something like this, of K0n. They're going to have something else here, plus constant, and here is the correlation function K0n. You might as well say, okay, I'm going to find some RG scheme and forget about that guy, but you still have the constant guy. And then you say, oh, then I'll just, to eliminate the conformal killing group divergence, just divide by the log absolute. That's what you might have thought. And this works for the disk. The disk doesn't have a log divergence. The disk only have this guy, quadratic. But it turns out that this thing here has its own log divergences.
Mm-hmm.
So it's not just that the log divergence of the SL2C, this is fake divergence, if you will, a fake divergence, not real, in the sense that log divergences, usually denote something real happening, like a physical amplitude and a particle becoming on shell in the sense of quantum field theory. So this guy has its own log divergences that should be combined with the log divergence of this L to C in one consistent manner, and the 1 over log will not work, but rather del by del log will work. Okay, this is in a nutshell, really in 3 minutes, the reason for the del by del log epsilon prescription. Okay, we'll get into that. That 1 over log will only remove this L to C log divergence, which is fake because you should actually fix 3 points to get the amplitude. But those guys also have divergences, and so consistently I should do del by the log epsilon prescription because this is RG invariant. It connects very well with the RG equation that you and I have been talking about. Because if I do del by the log epsilon prescription, right, of the partition function as a generating function, for example, K0, right, then this will connect with beta functions. Of del phi by del log epsilon. So I'm getting ahead of myself, but that's the point. Okay, so let me say that. Most importantly, he's telling us here, Polchinski and Liu, that on the sphere, you're going to get quadratic divergence from the region where all 3 points collide. Where all the 3 points collide. So if you take the limits where all 3 points collide, then you get quadratic divergence, but you get logarithmic if like 2 or 3 points. And this is the regime that we're going to be interested in the starting point of Riccati-Tetlin's prescription. Now, using operator product expansion of any 2-point and 3-point function, I can put these divergences, right, in the form of the R goes to 0 part. This is the limit where R goes to 0, so R is like small, right? I think of this as dz by dz, like basically this is standard. Z is a coordinate on the world sheet, okay? And what you're looking at is the Schwinger propagator.
Right, the proper time representation.
This is the proper time representation of the Schwinger proper time propagator, which is even for the particle, in the particle limit, is as close as you can get the string, is the word line formalism. Okay? So what you're looking at here is the particle propagator, 1 over p squared plus n squared, if you have this, and this is dr by dr, and the limit of r goes to 0, and it can be put in this form, in the form of, and of course, here you usually go to infinity, and you can put it in a form where basically it looks like this. Or actually 0 to 1.
Right, because we've
and here you go 0 to infinity of ds e to the minus s L0. Let me
let's just run through these identifications.
put this all away.
Yeah.
Right. So good. So let me
let's break this down because I think this is very important. Yeah.
Let's break this down. Take alpha prime here to be 1. We don't care about alpha prime at the moment. Yes. So dr by dr, I can express it as ds, which is Schwinger standard for Euclidean Schwinger parameter, right? And you can get to e to the minus s times L0, where L0 is going to be the string theory Hamiltonian, right? The generator
Yes,
file.
yes.
So
For the free string, yeah.
The free string. So I'm going to write here even sp squared to be consistent plus m squared.
Yep.
So good. And so you can see that we can get several kinds of divergences from this propagator. Right? And so you can see this is a so all divergences in string theory are IR, can be given an IR interpretation in target space. In other words, this is known in string theory. UV divergences on the world sheet correspond to IR divergences in target space. So he's saying, okay, even this fake conformal killing group divergences, these fake divergences, because I did not fix 3 points, as I usually should, I'm going to put a cutoff and take the limit as 3 points collide or 2 points collide in an endpoint function. Then I'm going to count the log divergences or quadratic divergences. Then I can represent them using the Euclidean Schwinger propagator formalism, proper time formalism, as any IR divergence in string theory over moduli space.
Right.
Okay. Now, here's shout out to the string field here. Because if you're with me right now, this is the one point where Setlin's, Arcadic Setlin's formalism connect on the world sheet to the story of a degeneration of tubes in endpoint correlation functions. What we're looking at is a tube generating function. It's a tube that is near the degeneration limit, except that this is crazy because on the sphere we learn that there's no such thing as 1 or 2 point function of degeneration. We just basically deal with on the sphere because the dimension of the moduli space is 0 until you get to endpoints on this world sheet. You basically are dealing with degeneration of tubes that look like this. So these are basically degenerating sphere with a long tube. Basically, this means you're near degeneration. And on the sphere, you only can have 2 here or more on each side, a left-hand hand, or 2 or more in each side. Usually that's on shell string theory. And this tube is infinitely long, and this is basically the log divergence of the Schwinger parameter.
Right.
When p squared plus m squared goes to 0, let's see what happens here. Let's take a look at this form. When p squared plus m squared is equal to 0, e to the minus s, the exponent gives 1, and you're left with an infinite divergence, basically ts, or in the dr cross r, this will be a log divergence. So this thing here is infinitely long, unless I decide to basically regulate the leg, the degenerating leg. This corresponds in field theory to the 4-point function. This will be a vertex, propagator, vertex in some channel. And then this will be the string theory version of it. If I decide here to say something, to put something O of log epsilon, some order of log epsilon, then the length of a tube will be log epsilon. And this is true when only we have two insertions here or more. But what we're saying here is that even in the 0, 1, 2, right, insertions, that we have a log divergence. These are the types of divergences that appear in this object for n greater than or equal to 4. Normal 4-point functions, divergence. These. Suppose n equals 4. However, I have this nasty guy, and I should also think of it as a tube. So before I connect with 4, I'm going to have something else appearing here. Maybe 1. When 3 points collide or 2 points collide, and we discussed this is the content of section 5 and obvious.
Yes.
So where we connect with multiple tubes. So now there's one. At the end of the day, when we remove the extra tubes, we're going to end up with this standard log divergence. And this log divergence is a physical pole, because it actually signals the appearance of particle coming on shell when p squared plus m squared near 0. But this one is a fake divergence that is always there. Does that make sense? It's always there. It's not signaling any particle coming on shell that was previously off shell. No, it's just a log divergence. And here's the word I want to use. They can always factor out of any n-point amplitude. So any k0n, by integrating over all vertex insertions, you can factor out such a log divergence. It's always standing there. And therefore, it should be treated not as, well, we're talking about two kinds of degeneration of tubes. This is called generic degeneration, and there's something called special degeneration. Special degenerations are degenerations which have to do with dilaton tadpoles and quantum mass renormalizations. But these are only true for genus G greater than or equal to 1. These special degenerations, because they're dilaton tadpoles and quantum mass renormalizations, and they happen only when
they're like X. You need the
only when this is true. Exactly. Only when. So, for example, something like this happens. So we have 1 on this side. That's called quantum mass renormalization. This will be treated by quantum mass renormalization. This is the subject. So the quantum mass renormalization. But there's also the more critical one, which is a dilaton tag, where you have nothing here. For massless particles, this is automatically on shell. This is always on shell, right? Because of the conservation of mass the conservation,
right.
The momentum, right? It's always on shell. There's no limit where it's off shell in some region of momentum space, and then in some region it becomes on shell. Similarly, it's the same thing for quantum mass renormalization. This is only true in on-shell string theory for genus G greater than or equal to 1. The sphere in the Arcadi-Zetlins prescription, where they integrate over the 4 index insertions, they have this feature and that feature. Crazy, right? I mean, this is true. They have these degeneration limits because we don't fix 3 points. They share this feature until we remove them by the del by the log epsilon prescription. The del by the log epsilon prescription removes these fake divergences. And so they're only left at the end with the physical log divergences coming from actual particles coming on. But they all share that they are log divergence. And when I have a log divergence, I should treat them consistently on the same footing under the ring normalization group. So RG, Callan-Semantic equation, will not tell you the difference, will not be able to distinguish between a log divergence that is fake, coming from a conformal killing group, or whether it's physical from an actual particle coming on shell.
Right.
And if we actually calculate the conformal killing group, let's go over this. Okay. So what they do is that they parameterize the conformal killing group on the sphere. It's the projective SL2C, to be precise. As follows: A dot sigma poly matrices. Of course, they act in the complex plane. As usual, it is the Mobius group, right? SL2C group, Mobius group. And it takes a point Z to Z prime. As usual, Z goes to Z prime as AZ plus BC over D. We'll come back to these points, by the way, of degenerations and this. We can spend a couple of episodes here just in this point and how it happens. But let's see. Okay, so then in particular, now they use a measure. Now we need to see what measure to use to calculate the volume, right? And you can see it's SL2C. So in the SL2C, they use some invariant group volume. They basically use the range of integration that gives you over a double cover. Sorry, a single cover. I'm gonna take it back. Single cover. So if you take a look, you'll see that yeah, good. So here is the volume. This is basically the volume of a sphere for pi r squared, right? So you do a volume element, which is D3A, D3B. I'm focusing on SL2C, not SL2R. But
right.
So D3A, D3B. And let me remind you what they are. A is like a three. It's a vector. So it's a vector points. A vector basically. So sigma is sigma 1, sigma 2, sigma 3.
Right.
Sigma, and this you get the dot product. You see the standard notation of quantum mechanics, right? A dot sigma, B dot sigma. And when you do this integral to give a single cover, what you end up getting is basically this. Sorry, I'm gonna do this. Sorry, take that back.
That's all good.
So what do you get? You get this. Notice, right. No cutoff has been imposed yet. But more importantly, man, the important is The difference, why the disk is easy, why the disk is cool, why the disk is a soft dilettante pairing, is because the disk does not have this term.
Mm-hmm.
This B term, this integral over B, the extra piece that is not right directly over B, which is going to be precisely the cutoff. This is going to be the log divergence. So the log divergence comes because of this B. So this B is going to be the log divergence, right? Remember, we're putting a cutoff now on the SL to C, but the cutoff on the SL to C, Polchinski and Liu are telling us here that if I do the integral over the sphere, not the group, the sphere with a cutoff, and integrate over all points, and take the limit for 2 and 3 points colliding, then I basically get what? The log divergence precisely of the SL to C. So it's as if putting a cutoff on the manifold and regulating the manifold is the SL to C volume is precisely what you would get if you put a cutoff on the sphere itself and taking the limits of 2 and 3 points. This is a critical point to understand.
Right. And we should know that here we're just doing a volume integral, right? Just integrating volume over the group manifold, versus the other thing what we're doing is analogous but not quite the same. We're integrating over positions of like operator insertions on the sphere with some cutoff, physical cutoff, literally like a shell.
They give us precisely the same result, and this was noted here and used by a credit, as I mentioned before. Here's the key point.
Yes.
The integrations over positions, and again a repeat diverge, and this divergence is exactly that of the conformal Killy group volume. Very, very, very critical and very important to emphasize. It's not intuitive. There's a manifold and this is a sphere. These are integrations over positions of vertex insertions, and these are volume divergences over the SL to C. The SL to C. So now, if you go over the integral, you say, now I need to impose some cutoff. At large values of B, that is when, right, the separation between typical points of the complex plane is reduced by a factor of e to the minus 2b. So then if you say e to the minus 2b is like epsilon, then you say that means that log epsilon is basically like b. When you come close enough, that basically says that log epsilon here is like b. And therefore, when you evaluate it, you get for the volume of the SL to C, the regulated volume of SL to C has a quadratic divergence piece, which we can forget about in RG sense. But then we're left with a log divergence coming from the integral, from the regulating the SL to C, and putting, instead of infinity, we put a log divergence here. Which is the log divergence. Which this does not have. So this is the volume of SL to R. Now, according to Polchinski, this is power law divergence. If we forget about the power law divergence, then the volume of the disk, the SL to R, is minus pi squared over 2. That's a finite renormalized value. Whereas the sphere, because of the log, it vanishes. And this value minus pi squared over 2 has been checked in recent papers. Very, very been looked at and studied and checked by Lorenz, Eberhardt, and the IS. Shout out to Lorenz because he explained a lot. This to me and Google, please. Again, we've had a long check, so we explain a lot of this to me as well. We have long conversations. about this. So shout out to both of them. Thank you
Awesome.
guys for interesting discussions with you and explaining a lot of this to me. So but that's the point. The disk has this interesting soft dilaton theorem that says that the partition function is equal to 1-point function, and you fix the ratio, fix the coefficient. Well, what fixes the coefficient on the sphere? This will have to wait. This ambiguity will have to wait until I explain a little bit more about my work with Aaron in another paper. But this is the engine of the del by the log epsilon prescription. And why we need to take, where is the log epsilon coming from? You can understand it in any way you like. You can understand it in terms of tubes, the length of tubes, degeneration tubes of scattering amplitudes like this. You can understand them all log divergences coming from points colliding one another on the world sheet. You can understand them in any way you like, right? The point is the del by the log epsilon prescription is a prescription to remove log divergences coming from correlation functions that does not differentiate between the log divergence of this L2C, which is fake, and the physical log divergences comes as points come on shell in actual scattering amplitudes in a way that was consistent with RG, in a way that makes everything works beautifully. And at least this is what Arkady Tsepnin will tell you in his papers. It needs checking. We could verify it. And we're going to tell you more about the gauge orbits. Now, Ed and I, to give you a heads up, we explained this Z by log epsilon using gauge orbits, especially in the second prescription of Tetlin, which we haven't discussed, gauge orbit story. And this is the, again, part of the story in the section 5. We'll know why precisely the del by the log epsilon works, because it picks the universal coefficient of the beta function. So we explain why it works. We'll explain the factorization of K0n and endpoint amplitude on this always log divergences. And then we'll move on maybe to explain how to recover in particular limit when log epsilon goes to infinity. Remember, when epsilon is very small, this goes to infinity. And this goes to infinity is what we define as an on-shell limit, because if this is allowed to go to infinity, then p squared plus m squared is equal to 0, and we really have what we call the on-shell limit, a particle coming on shell. Right? But a particle coming on shell has a divergence associated with it. It's not for free, because we have this infinity. How do we deal with the infinity when the particle comes online, or the particle comes on shell? Right? Because if I allow epsilon to go to 0 here, then this goes to infinity. Oh, so physically on shell, there's an infinity that I have to deal with. And I tell you how to deal with it precisely using the Euclidean S matrix of in Arkady's formalism. But we also, Aaron and I, go a step further, and we use the Feynman I epsilon prescription in string theory and string field theory, which is basically something that Whitten wrote the paper on back about 9 years ago in 2013. And we covered what we call the Lorentzian S matrix in the limit where epsilon goes to 0. So the point is, even on shell, when epsilon goes to 0, there are divergences that we're going to have to deal with. And we on shell, even when those guys are on shell, these are 1,1 basically. When I say on shell, means the insertions are all 1,1.
Right.
These satisfied by the vertex operators are Weyl invariant. They're not h comma h. They're 1,1. There are divergences associated with the tubes, and we show how to recover the right limits in the paper when we will discuss that at some point in the next episode. Well, I think this is a good point to stop it, and then we continue.
No, for sure. Well, thank you, Amr. No, this was
Absolutely.
very helpful, and this
My pleasure.
lays the ground, as you say, for all the stuff to follow. And I think that yeah, it was good to sort of take this detour to sort of come back, because indeed, as you kept emphasizing, it's an issue that the RG approach wouldn't be able to tackle by itself were we to use the wrong object. So if you say that you have a
Yeah.
logarithmic divergence, is a logarithmic divergence. It's mistakable for well, what you would normally think it is. It's mistakable for genuine running of couplings. It's mistakable for, a sort of regular kind of renormalizable, like why renormalizable perturbation theory normally works, and why RG works in that context so well. So it is very important to first identify what the right thing is to then go and play with, and it is fascinating that it does fall on this structure that Dolan noticed,
Yes.
which
Yes.
in these holographic applications
Mm-hmm.
is very important. It's very interesting because that in many ways this Dolan style prescription gives you the bulk Hamilton constraint. Like that really is, because that's the object that generates local RG transformations, and it directly gives you, if you could
Mm.
compute it, what the bulk Hamiltonian would be, in the sort of radial direction. So it's very fascinating to see
Interesting.
that that arises. Now, of course, this T2 prescription is even more fascinating. That is a second order thing, which I think is a bit of a novelty. But again, what that reminds me of is work by Friedan having to do with something called the lambda model, which I think you're aware of too. And there he sort of, in a sort of very sympathetic vein, he asked the question, okay, how would one derive effectively what the off-shell structure is in the target space without just matching what effective field theory reproduces the S matrices you compute by taking vertex operator correlation functions.
Are you talking about the very old paper by Fried? Because it was shout out to Frieden because he was the one to basically notice that the sigma model is connected to gravity back
No,
in
no,
1980 in his PhD
right.
thesis. Very
Yeah, yeah,
nice
yeah.
PhD thesis. So,
Yeah,
but
that,
it's
that that's
different.
that's
Yeah.
the original, no, for sure. But I mean, even like relatively recent, I mean 2000s, like early
Okay.
2000s. He had this
Okay.
this work on what he called the lambda model,
Done.
which
Mm-hmm.
basically he I think he just stumbled into some version of this T2 prescription and said, well, you see, this thing is
Mm-hmm.
kind of a diffusion equation. So, well, what is the stationary measure with respect to this diffusion? Well, it has to be the Gibbs, like, the Gibbs factor for the stationary distribution has to be the off-shell action. It's kind of the logic that went behind
Oh,
that.
oh, oh.
I mean, we can briefly open that paper because it's been a while since I thought about it, but I think this is exactly what he's doing.
Interesting.
Let's see. The degenerating tubes are also a feature of, starting point of what he talks about.
Oh.
Here we
Mm.
go. So he calls it tentative theory of large distance physics. There's a lot of
Mm.
explanation. I mean, it's a very big paper.
Yes, yes.
There's a lot of explanation having to do with his motivations, but his ultimate goal is to say, well, how do you get this? In fact, like, okay, say you started with well, not this, but like, say you wanted to really understand where as you were saying, the path integral and the bulk comes, the target space comes from. So he says, okay, now let's run through an exercise involving somewhat similar notions as what we were describing here. And okay, I'm scrolling quite a bit, I know, but basically the effect is to say that from the motivation that is very similar to what you sketched out, because you see
Mm-hmm.
this is effectively the same kind of log divergence that he's treating.
Yes, the two
um
handles colliding. Yes, yes.
yes, so he says there's generalized scale invariance. So let's go to see what exactly that means. There's an actual diffusion type prescription that he identifies somewhere. So there's a lot of talk, but like, I just want to bring you to this. Yeah, so he talks about the so-called a priori measure. And he says, okay, how do we get this a priori measure? And you see, there's this driven diffusion process that comes from taking these double derivatives with respect to couplings with a certain effective target space metric. And you see, if you had something like this T2 prescription, this is exactly the kind of thing you would be led to at the level of some measure. right? So at the level of some kind of a
Mm,
priori measure. And he says, okay, then you can work out what the space-time action principle should be. See that, no, it's the same kind of thing as what Zeitlin is describing,
yes.
right? You have the functions generating the beta functions, the C function. And so, well, the stationary point of this driven diffusion process, as you normally find, is the one where you take off one derivative effectively.
Yes.
And well, what is the solution going to be? Well, it's the thing that involves the integral of the beta function with respect to the cutoff, like this kind of flow integral, which, because
Absolutely.
of the gradient property, has to be the thing that generates the gradient. So, I mean, I'm not 100% sure this is T2, but it has a very similar feel to it.
Yes, it has actually, as a matter of fact. Yes. Yes. And in general, the fact that the partition function is an integral over the beta functions, I mean, like you pointed out, basically integrating over the anomaly. And so
Yeah,
he wants
exactly.
to see that, and we know that. I'll tell you, the symbology, it's okay. Connecting back to what we were saying before, we know that the sphere partition functions, this is something that we'll probably mention in the next episode. We've been talking about the central charge action, right? The off-shell action of the sphere is called the central charge action, right? The central charge action of the sphere is the same as the sphere effective action.
Yes.
So the sphere effective action that we talked about today for the Z0
Yes.
is precisely the central charge action that you and I discussed before,
Right.
which is the string theory or the sigma model C, which goes into the string theory C theorem of Samologikov, which includes the dilaton, right?
Right, right, right.
But we know the title of Samologikov's paper. It's irreversibility. It's a diffusion equation.
Yes, yes.
Whenever we have an RG flow of some object, which is in this case the central charge action of the sphere, because the sphere action is the central charge action, it's a diffusion equation. The RG flow, you're diffusing in RG space. So there is a diffusion structure in RG space of the effective action until you get to the fixed point, which
Right.
is a local minimum. So in fact, this is the title of the gemological paper was irreversibility of RG flow or something like that. But that is a feature of any sort of flow equation because it's a flow equation.
Right.
So he's extracting something nice about it, something more intrinsic, uh, as a diffusion or a heat equation or diffusion equation, which is and view an RG equation as such. And I think this is the mainly I'm not the underlying message in this lambda model paper. I think so,
Yeah, I mean,
which
it's
makes a lot of sense.
right, right. I mean, there's quite a bit in it. I mean, as we saw, it's a very, very big paper, but it is indeed very much related. And I think that, yeah, I mean, it would be very fascinating to see what role it has to play.
Absolutely.
And I mean, no, this is very interesting, very exciting because we're really getting to, we're getting to see how the sort of real identity of even perturbative string theory as we have it is being revealed on a very similar level to how we think about our regular kind of theories of the gravitational field, like general relativity plus other corrections. I mean, okay, I mean, it's still inherently perturbative if you think about it from the quantum perspective. As far as one can compute, you can only really
Mm-hmm.
compute some corrections, and EFT, it's not very predictive. That's kind of the downside of it, but that's in effect, there's nothing more non-perturbative about general relativity, despite its background independence, than what we're seeing here. And I think that that's a very important point because it'll guide us. I think this will really guide us as to how best to think about this, especially when we want to move forward with making relations with holography and so on, where you see there's a little bit of a hint of what non-perturbative structure could look like, right? When we talk about holography. So I think that, yeah, this is very good that we're sort of chugging through this at the rate at which we are. And yes, let's definitely reconvene next time, and dive into the details of what you and Aaron have managed to do
Yes, absolutely.
and
There's a
how
lot
you
more to do.
contextualize the
Yeah,
stuff. Yeah, I know, absolutely.
absolutely.
Looking forward to that, Amr. So for
Absolutely. Thank you
about
so
this
much for the
part,
opportunity.
oh
Appreciate
no,
it.
thank you, Amr. So yeah, I mean, for people that haven't, please like, share, subscribe, and comment, and I'll catch you all next time.
Thank you. Thank you. Thank you.